Okay, so you can see the solution of that one. That will be on the video. Okay. So let's just find a different, is there another question? So let's just find a different one for setup here. So maybe this next one will be good. I want to do one that's dy. How about the yx? Oh, there was no dy? The whole thing? Well, all I'm looking for is, it doesn't have to be that this problem. All right, this is good. We can do this. So here's y equals x squared and y equals 3x. That'll work. It's supposed to be straight. So then we can say that this is R is the base of a region, or a solid, base of a solid, whose cross sections parallel to the x-axis are right triangles. Okay, so what does that mean? It means that we're going to come along here, and every cross-section like this, that's going to be the leg of a right triangle. I should say isosceles. Okay, so that means that the height of it is the same as that. Okay, so the height of it, so I'll just draw it like this. So imagine that's perpendicular to the screen, okay? So that right triangle should be coming straight out at you. Okay, that's perpendicular to the screen. So let me see if I draw it better here. Oh, it's going to look just the same. I don't know if I'll be able to successfully draw it well, but the point is that this should be perpendicular to the screen, coming straight out at you. Okay, it's not. This is not parallel to the y-axis. Okay, so every cross section that you get is a triangle like that. So it's going to look something like that. And so then what is this dimension here? That's going to be your x2 minus x1. So x2 would be square root of y. So I'll write it down. So it'll be x2 minus x1. But then that's also the height, because it's isosceles, right? This is also x2 minus x1. So the volume of this thing is, so it's a triangle, 1/2 base times height, but they're the same. I'll just write it out twice. Base 1/2 base times height times delta y. And so it's going to be, but the base and the height are the same. Okay, so then you got, So x2 would be the x-coordinate on this in terms of y would be square root of y. And then the x-coordinate of this in terms of y would be y over 3. So let's go ahead and write it squared now, because they're the same. And then delta y. So that's your delta v. That's your little element, your little triangular element that you're going to add them all together when you integrate. Okay, questions on that setup? So it will be, in the end, it'll be, so we're going to integrate y from 1 to, is that 3? 9? 9. X, so this is the point 39. So you're going to integrate from, no, y is going to be 0. So sorry, my fault. 0 to 9. And we're going to add up all these triangular elements. 1/2 radical y minus y over 3 squared. So 1/2 base times height, dy. And that's a 0. So that's the volume of this thing whose base is that moon shape, and then every cross section this way is a triangle whose base is the same as the height. Right triangle. See how it works? So you have a couple of those in your homework. Questions? Okay. Ready for your quiz? How much you can do? You might not need it. Teach it. I'm just going to do it. All right. So x equals y cubed. It's like that. Y equals 1/4 x is like that. That's the point 8, 2. And then of course 0, 0. Okay. And then if we're going to rotate about this line, so let's do dx first, I guess. So it'll be a strip this way. Rotate it about y equals -5. You'll get a washer. So it's going to be the volume of the washer is going to be pi r outer squared delta x minus pi r inner squared delta x. So it's basically the big pancake minus the little pancake. And then outer radius is going to be, say, this y plus 5. So it's going to be, say, y1 plus 5. And the inner radius will be y2 plus 5. It was supposed to be a 5. It didn't turn out to be a 5. And so y1 is the y coordinate of this, which is cube root of x. So this will be cube root of x plus 5 squared delta x minus. And then the y coordinate of this line will be 1/4 x. Integral from, so that's going to be from 0 to 8. 0 to 8 of pi cube root of x plus 5 squared minus pi 1/4 x plus 5 squared all dx. So that's washers. Those who were successful, agree? Lots of nods. Okay. The other way would be then, what, delta x? Sorry, delta y, and that's going to make shells, right? That's going to make shells. Okay, so shells, I'll do blue, are going to be 2 pi r h delta y. This will be the height of the shell, and then this will be the radius of the shell. So the radius is just going to be y plus 5. It's the same y coordinate for both curves, so it's just y and then plus 5. And then the height is going to be x for the line, so x2 minus x1. So it's going to be 2 pi radius y plus 5, and then these in terms of y, because we have delta y. So x2 would be x in terms of y, 4y, and then x1 would be y cubed. So this will be dy, and then we'll be from 0 to 2 pi y plus 5, 4y minus y cubed, dy. They're all multiplied. Yeah.
So the strip is vertical. Is it always with respect to x?
Yes. Yeah. If we're in conventional rectangular coordinates and you do a vertical strip, then the thickness of that strip would be x, delta x.
Okay.
And then if you do a horizontal strip in conventional coordinates, then the thickness of that strip will be delta y. Yep. Other questions? Okay, so we're going to move on to the next stuff here, which is arc length. Yeah? Other question? Oh, Jason. So let's just talk about where we've been. So we started in the first week, and we said that the integral of bits of change of some quantity, say q, meant add up all the bits of change of that quantity, and then the result would be total change of q. That was our fundamental theorem from the perspective of quantities, rate of change in quantities. And so we were adding up k delta x plus k delta x plus k delta x, and we said those were each a bit of change, and if you added all those up, you got the total change. Okay, then we started doing some geometry, and then we said the sum of areas of rectangular slices of a region. If we added up all the areas of these rectangular slices of a region, what did it give us? The total area of the region, right? So total area of the region. Okay? And then we said if you did the integral of volume of a typical disk, typical pancake or washer, we got the total area of a solid. Volume. Okay, so now what we want is to get the total length of the curve of a function. So what are we going to do? We're going to integrate. Integrate what? If we want the total length of a function's curve, say from one x value to another, then we're going to integrate what? What do you think?
But it would do tangent lines.
Not remotely. Well, but the principle. So we're just going after the principle here. So what are we going to integrate to get the total area of the curve? Yeah, little bits of curve, right? Little bits of the curve. All right, but actually not little bits of the curve. We're actually going to make it easier on ourselves, we're going to do little line segments that approximate the curve. And then when we make those small enough, they'll be the curve. Okay, so little lines just approximate the curve. But when we make those line segments small enough, we'll essentially be approaching or have a total length that's indistinguishable from the length of the curve. Okay, so that's what we're going to do the rest of tonight, is work on this idea here. Okay, so we're gonna derive this formula for arc length, and it's very manageable and attainable for you guys. So it'll be, this derivation and understanding all the parts of the derivation will be assessed. Okay, so because it's not hard, so we're gonna do it. So we have this function. Okay, and it's like this. And say we're interested in starting at a, x equals a, and ending at, say, x equals b. We want to know how the distance of along that curve, along that arc. What is that distance? And this could be any function f. Okay, any function. So like we said, we're going to, fortunately, okay, that's better. Okay, so like we said, we're going to break this thing up into segments. I'll draw a different color so you can see it. Segment 1, segment 2, segment 3, etc. Okay? And we'll call each one of those S for segments. So delta S1, delta S2, delta S3, etc. So there could be a lot more than just 3 of them between A and B. But in order for you to see it, I can only fit 3 in there. Okay? So what are we going to do? We're going to sum up, remember, sum up as j equals 1 to n is the total number of segments, each of those lengths of those segments. And that would be an approximate curve length. Will it be too short or too long, the approximation? Too short or too long? Too short, because we're cutting the corners, right? We're going in a straight line from point to point, but the curves will be a little bit greater than those straight lines. So when you add all of those segments up together, it'll be too small. But if we take more and more and more of these segments closer and closer, with the points closer and closer together, we'll get to a point where the sum of those segments is indistinguishable from the length of the curve. Right? It'll be so close that it'll be the same. Okay? So how are we going to do this? So we need the length of each of these. We need this delta S, say, we'll use S2 as or S1 as the example here. How can I get the length of that straight line right there? Distance formula, which is based on Pythagorean theorem. So we're going to make a little right triangle. And for delta S1, we're going to have a delta X1 and a delta Y1. So now we can easily write what delta S1 is, or just, for that matter, delta Sj. So delta Sj by the Pythagorean theorem is going to be, so delta Sj squared is going to equal delta Xj squared plus delta Yj squared. So therefore delta Sj is square root of, this should be very understandable. And so this is for any segment, right? The jth segment. J goes from 1 to n, where n is the total number of segments. So j is just the jth segment, so it represents all of them. Any particular one or all of them. Okay, and so then we're going to sum all those up, right? So it's going to be the sum of all of these segments, which are the hypotenuse of these right triangles. So this is now the integral is taking form here, right? Because we know the integral is sum of all the little bits. And this is exactly the same thing, sum of all the little bits of segments. Okay, so, but we know with an integral we're going to need, if we're going to go from x equals a to x equals b, we're going to need dx as part of the deal, right? So we're going to do a little trick here. We're going to multiply by 1 in the form of delta xj over the square root of delta xj squared. So you should recognize that that's just 1. It doesn't change the value of what we've got because we're just multiplying by 1. Because the denominator is just delta xj, so we have delta xj over delta xj. And so we're multiplying that whole thing by 1. And then what we're going to do is, so now that we've got square root over square root. So we can do one big square root with all this stuff inside. Do you see? We'll do one big square root with all this stuff inside, and then it's going to leave our little delta x out here, which will eventually be our dx. Okay? So one big square root with all that stuff inside is going to be delta xj squared over delta xj squared. Plus, and then we're going to have delta yj squared over delta xj squared. And so can I do two steps at once here? Can I make that all one thing squared? And then times delta xj. Just delta xj, which is staying here from the numerator of this. Okay, not bad, right? Again, what did I do? I multiplied by 1, then I grabbed this thing that was square root and I combined it with that and left this out here. And so then this term will go underneath that, and this term will go underneath that, and that'll be delta yj over delta xj quantity squared. Okay, getting close here. So first thing becomes square root of, what's that? 1. Anybody recognize what this is? So delta y over delta x. Okay. So as delta x gets very small, That is, yes, that's the derivative. That's the derivative of y with respect to x. It's the derivative. Some are saying tangent. Yeah, that's what. So yeah, that's the derivative. Okay, so we're going to write it one more time. So now we're ready to say, let delta x go to 0. So delta x is going to get very, very small. And when delta x gets very, very small, this becomes our integral. And we're gonna have it. We're gonna the length of the curve equals integral from a to b of 1 plus the derivative squared dx. And so what does that do? That finds the arc length with respect to x. So starting from x equals a to x equals b, it'll sum up all those little itty-bitty segments, right? Which will essentially be the same as the curve because the points are so close together. The difference between the arc and the segment will be so indistinguishable that adding up the segments will get us the arc length. Yeah, that's the derivative. That's the derivative. Okay, so all the principles involved in that, you should know and be able to reproduce this. This is pretty straightforward. Nice little derivation. Okay?
The only part I understand is what's the first step.
What's that?
The only thing I understand is how you come up with like the change in x day over square root.
Oh, it just because it works.
Just 'cause
So yeah. So
this is
you
like
do
a
it because it
proof
works. You wouldn't have to figure that out, but just understand what happened, right?
This is like a proof basically.
There's a proof. Yeah. This is proving that this formula calculates the length of a curve. Okay, so let's do an example. Other questions on this? Okay, so find the length of the curve. Y equals 1 plus 6 x to the 3 halves, x from 0 to 1. Okay, so we just got our formula here. So we could also write this as y prime, right? dy dx is also y prime, is also, if it's given as a function, f prime. So given that I have y, I'm going to write dy dx as y prime. It's the exact same thing, right? So what do we need to set this up? There's just one thing that we need. We need y prime. We need the derivative, right? Because the derivative is going to go there. So derivative is 0 plus 9 x to the 1 half, right? So 3 halves times 6, x to the 1 half. Okay, so then our length is going to be integral from 0 to 1, 1 plus 9x to the 1 half squared dx. Question?
On the test, is it a fair game to ask us just to recreate that whole formula again?
Yeah, you should know everything about that. Yep. Yep. Or I could ask you about a part of it. But yeah, the whole thing is fair game. So this turns out to be 1 plus 81x. And that's a piece of cake. How do we do the antiderivative of that? 1 plus 81x to the 1/2, 3 halves. No, antiderivative, not derivative, right? Antiderivative. We're going to need a 2/3. That would be like our first attempt, right? Our first attempt. And then think about taking the derivative of that. We'll also have, by the chain rule, we'll have a times 81, which we don't have here, therefore 1 over 81. Okay? And if you have been clutching to the U substitution, you're more than welcome to. And you'll get the same thing. 1 over 81, 2/3, 1 plus 81x to 3 halves from 0 to 1. And we'll get, what is this? 2 over 243. 82 to the 3 halves minus 2 over 243 times 1. So that value right there, what is the length of this curve if you graphed it, starting at x equals 0 to x equals 1. That's how long it would be right there. Okay, any questions? All right, so let's do something a little more challenging and actually slightly more interesting. So what we want to do now is we want to use this to actually derive, let's derive the circumference formula for a circle. We'll use this arc length formula to derive the circumference of a circle. So first let's put our circle on here. So if I okay. So first of all, we need a circle. We need what is, if we were to write a circle as a function, do we know how to write a circle as a function? Let's see. So we want to make it centered at the origin. That's the easiest. So can we write the top half of a circle? Can we just write the equation of a circle? So any circle, radius r, centered at the origin. What would that equation be? Anyone know? So it would be x squared. So we're trying to represent every point on the circle. So if this point is xy, right? Then this distance here is what? That's r. And so we can use Pythagorean theorem to write an equation that relates x and y, which would be x squared, base squared, plus y squared equals r squared. Therefore, y as a function of x would be, for the top half of the circle, square root of, so if someone said that before, good. So when we take the square root of both sides with the y, we're going to get a plus or minus. The plus is the top half of the circle, all the positive values of y. The minus would be the bottom half. Okay? So what we're going to do is we'll integrate as x goes from 0, x equals 0, which would be the top up here, to x equals, what's x equal right there? R. So we're going to integrate from 0 to r, and then we're going to multiply that by 4, and that should be the circumference of a circle, which is, what is the circumference again? 2 pi r. Okay, so this is what we're after. We're going to use the arc length formula to prove that the circumference of a circle is 2 pi r. We're going to do that by doing the arc length for a quarter circle, and then we should get 1/4 of that, right? when we do a quarter circle, what should we get? We should get pi r over 2. 1/4 of that. Okay, so here we go. So we're going to do, again, the integral from 0 to r of square root of 1 plus, okay, derivative. So we got to do the derivative here. So y prime is 1/2 so 1 over 2, radical in the bottom now. By the chain rule, we also have negative 2x. So it's going to be 1/2 that thing to the negative 1/2. So I just made it a square root in the denominator. And then by the chain rule times negative 2x. That's our derivative of our top half of the circle function. Good? All right, so we're going to square that. And so that'll be nice because we'll get rid of that square root, okay? So we're going to square, oh, and the twos go, right? We'll get rid of that first. So this, when we square that, it gets a lot friendlier, right? We're going to get x squared over quantity r squared minus x squared dx. Okay, so now we got to do some algebra here. So the first thing we're going to do is we're going to make this all one fraction. We're going to add these and get all one fraction underneath the radical. So we got a little work to do here, a little algebra. So common denominator is going to be r squared minus x squared. What are we going to have? We're going to have top and bottom by r squared minus x squared. And then this is just by itself. So it's going to be r squared minus x squared plus x squared. More nice things happening here. Numerator just becomes r squared. Right? Because minus x squared plus x squared is 0. We're just going to have r squared in the numerator over okay, then we're really close. So what do you notice in the numerator? We have the square root of r squared, which is just r. Okay, so we can do okay, we actually don't want to do that, and I'll show you in a sec. What we want to do is we want to divide top and bottom by r squared and make this a 1. Okay, that's what we want. We want a 1 there. So we're going to divide the top and bottom by r squared. Okay, so why do we do that? Because it works. Okay? So we're going to divide the whole top and bottom, both top and bottom by r squared. So we're going to get 1 over the square root of 1 minus x squared over r squared. Did you catch it? So we're going to do r squared over r squared at the top. That gives us a 1. Square root of 1 is 1. Then when we divide the numerator by r squared, we're going to get 1 minus x squared over r squared. Do you see it? Ask me.
Why does dx change to dr?
It does not. Okay, so then we're one step away here from something we should recognize. 1 over the square root of 1 minus quantity x over r squared. Who knows their derivatives? What is it? The arc sine. This is arc sine, right? Arc sine is 1 over 1 minus argument squared. So what we have is the arc sine of x over r. But there's going to be chain rule coming back the other way, right? So if we were to take the derivative of this by the chain rule, we'd also have, we would get, by the chain rule, we'd have times 1 over r, which we don't have a 1 over r here. So we're going to need times r. Okay, and then that's going to be from 0 to r, right? And we're expecting this to be, what, pi r over 2, 1/4 of that. That's what we're thinking. It's going to be 1/4 of that, which will prove that the circumference is 2 pi r. So here we go. We're going to plug r in, and we're going to get r times, what did I go wrong here? Sine inverse of 1. Okay, we'll just go with it. Sine inverse of 1. Okay, and then minus r times sine inverse of 0. I'm scared. What is the sine inverse of 1? Oh no, I think it's right. Sine inverse of 1, what, is the angle between negative pi over 2 and pi over 2 that would give a y-coordinate of 1 on the unit circle? Pi over 2, right? So it's r. This is sine inverse of 1 is the angle that gives you a sine of 1. What angle gives you a sine of 1? Pi over 2. What angle gives you a sine of 0? 0. Did it work? It worked. And that is 1/4 of 2 pi r. Check. Got it. So we proved that the circumference of a circle is 2 pi r by proving that 1/4 circle is r pi over 2. Yeah.
Why do you multiply by r?
This one,
Yeah.
it's like hold on a sec. It's like undoing the chain rule because we don't just have x squared. We have x over r squared.
Yeah.
So if you think about going backwards to take the derivative of this, you'd have the chain rule, and you'd do the sine inverse, and then you'd have times 1 over r, like the coefficient of x.
Right.
But we don't have the 1 over r here,
So you multiply by r.
so we need the r. So it's like undoing the chain rule.
Okay.
If you're not sure, just do u substitution and start with u equals x over r.
Yeah.
If you do u substitution, you'll do u equals x over r, and you'll have sine inverse of u. But then that r will come out. Okay, so for Wednesday there'll be web work and there'll be a short written portion too. You'll turn in written homework for Wednesday. Okay.